Now, starting with the halides of the group 16 elements. Group 16 elements, the halides. We have the compounds of oxygen with fluorine are called fluorides. Compounds of oxygen with chlorine are called chlorides and bromides, iodides in this way. Now, what you find is that the compounds of oxygen with fluorine are called fluorides, but with chlorine, bromine, iodine, we call it as that is nothing but chlorooxide, chlorobromide, chloroiodide. In this way we call it as iodide, chloride, bromide, iodide, but we call it in this particular way, chlorooxide, chlorobromide, chloroiodide, in this way, because their oxygen is more electronegative. Here fluorine is more electronegative than oxygen, so it is called as fluorides. Alright, compounds of oxygen with fluorine, because fluorine is the most electronegative element than oxygen. For example, the compound F2O is usually written as OF2. It is not written as F2, it is written as OF2 and is named as oxygen difluoride. Further, since oxygen is more electronegative than halogens, so hence it is called as halogen oxides. As I said you, that is chlorooxides, bromooxides, in this way we call it as. Now, next is we are having this sulfur, also same thing. It forms 4 types of halides, sulfur forms. It has got monohalides, S2, X2. X stands for fluorine, chlorine, bromine, iodine. You know that. S2, X2, it is monohalides. Then dihalides of the type SX2, dihalides. Tetrahalides of the type SX4, and hexahalides is of the type SX6, where only fluorine is coming. SF6 we can say that, fluorine is there. In case of hexahalides we have got fluorine. In case of tetrahalides, sulfur from tetrahalides with fluorine and chlorine only, and sulfur from dihalides with fluorine, chlorine and bromine only. Got it? Silurium and tellurium form fluorides in +6 oxidation state, whereas chlorides and bromides in +1, +2 and +4 oxidation state. Again I repeat, selenium and tellurium form fluorides in +6 oxidation state, whereas chlorides and bromides in +1, +2 and +4 oxidation state, we can say that. Now coming to sulfur hexafluoride, sulfur when reacts with fluorine it forms sulfur hexafluoride. It is a colorless, odorless gas. It is thermally stable. It is extremely unreactive and is not attacked by any of the chemical reagents. Due to chemical inertness and dielectric strength, it is used as a gaseous insulator in high voltage generators and switch gears. Alright, sulfur hexafluoride is used as dielectric, due to chemical inertness, it is used as a dielectric and dielectric strength, it is used in gaseous insulators, we can say that, in high voltage generators and switch gears, we can say that. So sulfur hexafluoride is octahedral structure, SF6 is octahedral in nature, and SF4 is trigonal bipyramidal in nature, SF4. It is also prepared with like sulfur chloride, compounds of sulfur, we can say that SCl2, when it reacts with NaF and heated it forms SF4 and NaCl. SF4 it's highly reactive compared to SF6. SF4 is highly reactive and is rapidly hydrolyzed by water to form SO2 and HF, we can say that. So sulfur of SF4 is in a state of sp3d hybridization. It is trigonal bipyramidal structure. Got it? It is trigonal bipyramidal structure. We are having it. Now elements of group 16 also forms different types of oxides like monooxides, dioxides and trioxides, we can say that. Like in case of sulfur we got SO, sulfur monoxide, which is unstable of course. Then sulfur dioxide SO2, sulfur trioxide SO3, sulfur heptoxide S2O7. Similarly in case of selenium, tellurium and polonium also we are having the different kinds of oxides, SeO2, SeO3 in case of selenium. In case of tellurium we are having TeO, TeO2, TeO3. In case of polonium we are having POO, POO2, we can say that. Clear that these are the different types of oxides of group 16 elements. That is, it forms monooxides, dioxides, trioxides, heptoxide. Got it? Heptoxide we can find in case of sulfur only, not in any other elements, we can say that. Sulfur, that is heptoxide, S2O7, we can say that. Clear? Sulfur also forms many oxoacids. Many oxoacids it forms. Let me say you. Oxoacids of sulfur are sulfurous acid H2SO3, sulfuric acid H2SO4, thiosulfuric acid H2S2O3, peroxomonosulfuric acid H2SO5, peroxo disulfuric acid H2S2O8, and that is dithionic acid H2S2O6. Alright, silurium and tellurium also formed oxo acids. We can say some important oxo acids of sulfur of selenium and tellurium is with selenium we got selenous acid H2SeO3 and selenic acid H2SeO4, and with tellurium we have got tellurous acid H2TeO3 and telluric acid H2TeO4. We can say that. The strength and stability of the oxo acids of group 16 elements decreases progressively from sulfur to tellurium. Sulfur to tellurium, we can say that the oxo acids of group 16 elements, the strength and stability of oxo acids of group 16 elements decreases. Alright, so in this way we find these are the different oxides, then halides and oxo acids of group 16 elements. We saw it. Now coming to the group 16 element, we are having oxygen. Coming to group 16 element, we have got oxygen. So what we find is that in case of group 16 elements, we have got the dioxygen, that is O2, rather it is known as oxygen also. So it has got some anomalous behavior. First of all, its anomalous behavior is due to its small size, small atomic size, is high electronegativity, the absence of vacant d orbital in its valence shell. Just like in case of what you can say in fluorine, we have seen it. Alright, that is its small atomic size, its high electronegativity and the absence of vacant d orbitals, due to which it shows anomalous behavior. So if you find there are some important difference between oxygen and some other elements of group 16, you may write it down this one. There are some important difference of oxygen with other elements of group 16. The first one, oxygen is a gas at room temperature, while all other elements of the groups are solids. Oxygen molecule is diatomic, while the molecules of other elements are more complex and polyatomic. While the molecules of all other elements are more complex and polyatomic, we can say that. Oxygen is paramagnetic in nature. Got it? Oxygen is paramagnetic in nature, while all other elements are diamagnetic. We can say they are diamagnetic in nature. We can say that. Due to its very high electronegativity, oxygen is capable of forming hydrogen bond with water, alcohol, carboxylic acid, etc. Due to its very high electronegativity, oxygen is capable of forming hydrogen bond, while other elements does not, because they are less electronegative in nature. Oxygen exhibits an oxidation state of -2 in most of its compound. In the absence of vacant d orbitals in its valence shell, it cannot excite its paired electrons and therefore unable to exhibit higher oxidation state, while other elements shows +2 as well as +4 and +6 oxidation state. Alright, in addition to -2 oxidation state. Then the compounds of oxygen are more ionic than those of the other elements of the group. We can say that. Next, oxygen is capable of forming p-pi multiple bonds. p-pi multiple bonds, while the other elements of the group does not show much tendency to form multiple bonds. Much tendency. Hydrides of oxygen, that is water, it's a liquid at room temperature, while hydrides of the other elements are gaseous. Hydrides of oxygen is liquid at room temperature, while the hydrides of other elements are gaseous. Now coming to oxygen, the preparation, you can see that we can prepare KMnO4. When it is heated, we get K2MnO4 and oxygen gas. Similarly, barium peroxide, when it is heated, we get that is barium oxide and oxygen gas, we are getting it. Similarly, potassium permanganate, when it is heated with sodium peroxide and H2SO4, you can see it on the screen. We are getting potassium sulfate, manganese sulfate, sodium sulfate, water and oxygen. We are getting it. Similarly, in the lab, also potassium chlorate on heating will give you, in presence of manganese dioxide, will give you potassium chloride and oxygen. Potassium nitrate on heating will give you potassium nitrite and oxygen. Alright. Similarly, mercuric oxide, you have done it in the lab in the lower classes. On heating will give you mercury and oxygen gas. Similarly, silver oxide on heating will give you silver and oxygen gas, we are getting it. Got it? Similarly, sodium peroxide, when it reacts with water, Na2O2 plus water will give you NaOH plus oxygen. In this way we are getting it, NaOH plus oxygen gas, we are getting it. So you can see in the screen here, I have shown you the lab preparation of potassium chloride with manganese dioxide. When potassium chloride is heated with potassium chlorate rather, it is heated with manganese dioxide, potassium chlorate 4 parts and manganese dioxide 1 part. It is heated in a hard glass test tube at around 420 Kelvin. We are getting the oxygen gas, where MnO2 acts as a catalyst in this particular reaction. You have done it in the lower classes. Actually, the temperature is required very high, but by using MnO2, the temperature is lowered to around 420 Kelvin, where oxygen gas is being collected by the downward displacement of water. You can see it. Clear? Now, coming to the properties of oxygen, you have read it in lower classes. Oxygen is a colorless, odorless, tasteless gas. It is not much soluble in water because it is non-polar in nature. It is absorbed in alkaline pyrogalal solution, oxygen gases. It is heavier than air. It is paramagnetic in nature. And coming to the chemical properties, oxygen reacts with several of the oxides to form higher oxides like SO2 plus O2 on heating at 720 Kelvin and 280 M will or platinum in presence of vanadium pentoxide will give you SO3. Similarly, ammonia when heated with oxygen in presence of platinum, that is in the nitric acid chapter we have seen it, that's catalytic oxidation of ammonia, it is said to be as, will give you NO plus water. HCl when it is heated with oxygen in presence of 700 Kelvin and CuCl2 will give you water and chlorine gas, we are getting it. So there are several other reactions are also being there, several other reactions like CH2 plus oxygen will give you, that is nothing but CO2 plus SO2, so to say, CO2 plus SO2. Clear? So in this way, when hydrocarbons is heated in presence of oxygen, we get it carbon dioxide and water, you know that. Carbon dioxide and water, you know it. Clear? So in this way, if you see the what you can say, one of the period I have shown you there, that is one of the particular period, that is your sodium peroxide. Sodium oxide is strongly basic. Then after sodium we have got magnesium, which is basic, aluminium, which is amphoteric, weak SiO2 is weakly acidic, then phosphorus is moderately acidic, sulfur dioxide is strongly acidic, and Cl2O7 is again very strongly acidic. That is the period 3 of the periodic table I have shown you there. If you move from left to right, it changes from basic character to acidic character. That is what I have shown you there. You know that you have studied in lower classes, that it changes from basic character to acidic character when you move from left to right in a period. That is what I am shown you there. So in this way, the basic character, in between we are having some amphoteric character we are having. Now coming to the several oxides of oxygen, we are having acidic oxide, basic oxide, amphoteric oxide, you know, acidic, basic, you know it, amphoteric also, you know it, means which possess the properties of both acidic as well as basic oxides, like your aluminium oxide, zinc oxide, lead monoxide, tin oxide. They are amphoteric in nature, we can say that they are amphoteric. Now coming to ozone, another allotropic form of oxygen, we can say that allotropic form of oxygen, ozone. Ozone is generally prepared when oxygen is passed through silent electric discharge, we get ozone gas. Got it? We get ozone gas, and the reaction is endothermic in nature. Silent electric discharge means sparkless electric discharge. Sparks will not be produced. That is called silent electric discharge. It produces less heat and thus prevents a local rise in temperature. Otherwise, ozone produced in the reaction will again decompose back into oxygen. So in preparation of ozone, you can see this is your Siemens ozonizer, the diagram which you can see it there. It consists of two coaxial glass, what you can say, tube sealed at one end. You can see it there in the figure on the screen. You can see the inner surface of the inner tube and the outer surface of the outer tube are coated with tin foil. You can see I have written there, it is written there on the screen, tin foil. The tin foils are connected to the two terminals of the power induction coil. You can see it is being connected. Power induction coil, that is your battery, and the pure dry and cold dioxygen is passed in the annular space through an inlet. You can see pure and dry oxygen is being passed through an inlet. Got it? When the current is switched on, silent electric discharge passes through the dioxygen gas present in the annular space and converts it partially into ozone. Again I repeat, Pure, dry and cold dioxin is passed into the annular space. You can see there on the screen. When the current is switched on, the silent electric discharge passes through the dioxygen gas present in the annular space and converts it partially into ozone. The mixture of ozone and oxygen thus obtained is called ozonized oxygen, which you can see it is coming out of that particular ozonizer and is taken out from an outlet on the other end of the tube. The ozonized oxygen contains about 10 to 15% of ozone. In this way, we are preparing what you can say ozone. We are getting ozone. Clear? So after that, ozone is being separated from oxygen and we are collecting ozone separately. We are separately collecting ozone. Clear? Now the central atom of ozone in ozone is sp2 hybridized containing a lone pair of electrons. As a result, ozone has an angular structure with a bond angle of 117 degree. Ozone is a very powerful oxidizing agent, second only to fluorine, but much stronger than oxygen. We can say that it is much stronger than oxygen. Now these are the several reactions of ozone. That is, when PbS reacts with ozone, we get PbSO4 acts as an oxidizing agent. HCl reacts with ozone to give chlorine, again acts as an oxidizing agent. Potassium nitrite reacts with ozone to give potassium nitrate and oxygen, again oxidizing agent. So these are all the oxidation reaction of ozone. You can see it on the screen. Ki reacts with it, potassium ferrocyanide reacts with it, then iodine reacts with ozone to form HiO3, phosphorus reacts with ozone to form H3PO4, antimony reacts with ozone in water to form antimony oxide, we can say that, antimony acid, we can say that, we are getting it. Mercury reacts with ozone to form mercurous oxide and oxygen gas, we are getting it. So basically ozone, what you can say, decomposes to give you oxygen gas at 573 Kelvin. 203 in presence of 573 Kelvin will give you 302, and as a result ozone decomposes also to give nascent oxygen, and this nascent oxygen helps in oxidation. Just now I said, the different types of oxidation reaction, it is the presence of the nascent oxygen only, it helps us, got it, in oxidizing the different compounds into different oxidized product, we can say that. Now the mercurous oxide thus formed dissolves in mercury, which loses its meniscus and starts sticking to the glass. This is called tailing of mercury, we can say that. The meniscus can however be restored by shaking it with water, which dissolves mercurous oxide. Now because of its oxidizing action, ozone acts as a mild bleaching agent, as well as it bleaches vegetable organic matter. Ozone, it acts as a bleaching agent, got it? It bleaches means it decolorizes several organic substances, colored organic substances. For example, if you take some red rose petals, it will bleach into form white color rose petals, you will be getting it. It bleaches in this way. Now it acts as the reducing agent also, ozone, at the same time. It's very interesting that ozone acts as both oxidizing as well as reducing agent. It gives you water and oxygen, we can say that. Clear? So in this way ozone acts as a reducing agent as well as oxidizing agent. Ozone reacts with ethylene to form ethylene ozonide. You have studied in what you can say in organic chapter this particular thing. Ozone, it is used for bleaching. Just now I said you bleaching oils, bleaching flow, there is starch and delicate articles. It is used in the manufacture of artificial silk and synthetic camphor. These are the uses I am saying you. Ozone is used as a powerful disinfectant and germicide in the purification of water. Remember it. Ozone is used as a powerful disinfectant and germicide in the purification of water. It is also used as an oxidizing agent in the manufacture of potassium permanganate from potassium manganate. We have seen it already, the reaction. Ozone layer, you know what it does. It protects the ozone layer. It protects from harmful radiations which is coming from the sun, and the depletion of the ozone layer, the destruction of the ozone in the atmosphere, which is termed as depletion of the ozone layer, is mainly caused by the nitric oxide, atomic oxygen, then chlorofluorocarbons and all these things which are used as coolant in refrigerators, air conditioners, etc. These causes the depletion of the ozone layer, and now the depletion of ozone layer is leading to the formation of ozone hole, which is hazardous to human health. That you know it, you have studied. Because of this only, the ozone layer absorbs harmful ultraviolet radiations of the sun, and which is reaching to the earth's surface, and we may suffer from several what you can say sunburns, skin aging, then leukemia, that is your cancer, cataract of the eyes, skin cancer, lung cancer, breast cancer, premature aging, Got it? So many other things we can have. The depletion of the ozone layer is mainly caused by, as I said, your nitrogen and CFCs. It is being caused. We can say that. Clear? So this is about your what you can say, oxygen and ozone. Thank you very much.